How does eventual consistency affect microservices deployments? Have you ever wondered how data remains consistent across different services in a microservices architecture? Today, we will discuss how eventual consistency plays a role in microservices deployments. Eventual consistency is a data consistency model that allows each microservice to manage its own data store independently. Instead of requiring immediate updates across all services, it allows changes to propagate asynchronously. This means that while all services will eventually reach a consistent state, there may be temporary discrepancies during the update process. In the context of microservices deployments, eventual consistency impacts several important areas. First, let's talk about scalability and performance. Since microservices do not need to wait for immediate synchronization, they can process requests independently and in parallel. This reduces latency and improves overall system throughput. Using asynchronous communication methods, like event-driven messaging or message queues, allows services to update their data stores without blocking operations. This supports high scalability, which is essential for modern applications. Next, we have resilience and availability. Eventual consistency aligns with the CAP theorem, which states that in distributed systems, you can prioritize availability and partition tolerance over immediate consistency. In a microservices deployment, network delays or failures can happen. Eventual consistency allows services to continue operating and accepting updates even if some parts of the system are temporarily unreachable. This design improves fault tolerance and keeps the system running smoothly. However, while eventual consistency offers benefits, it also brings complexity in data management. Developers must create mechanisms to detect and resolve conflicts that arise when multiple services update related data independently. To handle these challenges, patterns like event sourcing, command query responsibility segregation, and compensating transactions are often used. When deploying microservices with eventual consistency, careful orchestration of event flows and data synchronization processes is necessary. Services need to be designed to handle out-of-order or delayed events effectively. Deployment pipelines typically include monitoring and alerting to detect data divergence and ensure that all services eventually converge to a consistent state. Lastly, we need to consider user experience. Since data consistency is not immediate, users may notice temporary discrepancies, such as stale data or delayed updates. This trade-off is acceptable in many applications where absolute real-time consistency is not critical. However, it must be managed through thoughtful user interface design and communication. In practical terms, eventual consistency allows microservices deployments to achieve high scalability, fault tolerance, and independent service evolution. It supports the requirements of modern distributed systems by enabling services to operate autonomously while ensuring that data consistency is restored over time. However, developers must adopt asynchronous communication, implement conflict resolution strategies, and design for eventual convergence of data states. This approach is well suited for environments where distributed, scalable, and resilient systems are essential.